We interact with large language models every day, don't we? Asking them questions, getting summaries, drafting emails, even writing code. Their capabilities feel pretty amazing.
They absolutely do.
Mm-hmm.
But what you're experiencing often isn't just the raw power of that initial massive training they get,
Hmm.
on mountains of text data.
Right.
That pre-training phase is crucial. It's where they learn the structure of language, facts about the world, how to predict what comes next.
Right. They learn to be incredible predictors based on patterns they've seen, almost like super autocomplete.
Exactly. But predicting the most statistically likely sequence of words doesn't automatically make them helpful or truthful or, good at following tricky instructions.
Or skilled at complex reasoning.
Definitely not.
Yeah.
That initial training optimizes for probability, for likelihood, not necessarily for usefulness or alignment with what you, the user, actually want.
Okay, so the real shaping, the part that turns them into helpful assistants, that happens after that initial big training.
Precisely. It's the post-training phase. This is where the models are refined, guided, steered to become the tools we interact with.
And that's our mission today. We've taken a deep dive into a stack of sources, articles, research papers that explore this crucial stage, how LLMs are improved after pre-training, focusing especially on techniques like reinforcement learning and different types of fine-tuning.
Yeah, our goal is really to extract the most important insights from this material. We want to give you that shortcut,
Yeah.
to understanding how these models go from being merely statistically capable,
It's just good predictors.
right, to being genuinely helpful, aligned with human intent, and capable of tackling more complex tasks. And just to be clear, everything we'll discuss comes directly from these sources we've been digging through.
All right, let's unpack this. So the core challenge with just pre-training, as the sources point out, is that predicting the next word based on static data, well, it doesn't prepare a model for dynamic interaction.
No, it doesn't.
It doesn't teach it to follow instructions or pursue a specific goal over a series of steps.
Think of generating text not just as prediction, but as making a sequence of decisions. You pick one word or token.
Mm-hmm.
Then based on the prompt and that first word, you pick the next, and so on. Our sources describe this really well as a sequential decision-making process,
Okay.
much like you'd find in reinforcement learning environments.
Like training an agent in a game where each move is a decision.
Yes, exactly. In the LLM context, the state is the text generated so far. The action is picking the next token.
Got it.
And there's a reward that tells the model how good the overall sequence of choices was. For instance, was the final answer correct? Was it helpful? Was it, formatted nicely?
So instead of just picking the most likely next word, the model needs to learn to pick words that will eventually lead to a high reward for the whole response.
That's the fundamental shift that reinforcement learning brings. It's about learning a strategy or policy for picking actions tokens to maximize the total cumulative reward or return you get over time.
That's very different from just maximizing the likelihood of the next token given the training data.
Totally a different objective.
That sounds like it requires some trial and error, though, trying different paths to see which ones pay off.
Absolutely. A core idea in RL, which applies here, is balancing exploration, trying out new ways of generating text that might lead to higher rewards.
Mm-hmm.
With exploitation, sticking with the generation strategies you already know work reasonably well. This lets the model go beyond just repeating common patterns it saw in the pre-training data.
And the sources mention a few key RL ideas that come into play here, concepts we should know.
Yes, they touch on concepts like the value function, how good is a state, or the Q function, how good is taking a specific action in a state, and importantly, the advantage function.
The advantage function. That sounds technical. Can you break that down simply for us?
Sure. Think of it this way. If you're at a certain point in generating text, that's your state. The advantage function tells you how much better or worse a specific next word and action is compared to the average outcome you'd expect from that point onwards.
Okay, so better or worse than average for that specific choice.
Exactly. It helps the model figure out which specific choices were responsible for a good or bad final result, even if the reward signal only comes at the very end of the whole generated sequence. This is really crucial for learning in tasks that require many steps, like complex reasoning.
Okay, that helps. So how do you actually take these RL ideas, often used for like teaching robots to walk or agents to play games, and apply them to shaping a language model?
Well, the material we reviewed outlines a common multi-step process. It's particularly used in something called reinforcement learning from human feedback, or RLHF.
Or LHF. Okay, walk us through it. Step 1.
It usually starts with supervised fine-tuning, or SFT. You take the pre-trained model, the one that just learned from all that text,
Right.
and you train it further on a relatively small data set of high-quality examples written by humans. This data set typically consists of prompts and desired responses.
Okay.
This step gives the model a baseline understanding of how you want it to behave, the desired format, the style, the kind of helpfulness you're looking for.
So it's like showing it examples of good behavior first, learning by imitation.
Exactly. It learns by imitation to get the general shape and style right. Then, step 2 is building a reward model, or RM.
Okay.
So it's a separate model, and it's trained to predict how a human would rate a generated response. So you gather data by having humans rate different outputs from that SFT model we just talked about.
How do they rate them? Like on a scale?
Often it's by comparing outputs side by side, which one is better. That's
Yeah.
pairwise preference. Or sometimes ranking a list of outputs from best to worst.
So the reward model learns to predict human judgment. It becomes a sort of digital taste tester.
Yeah, it's a good way to put it. It becomes a stand-in for human taste and helpfulness. It learns to output a high score for responses humans liked and a low score for those they didn't. The sources mention methods like Bradley-Terry or Plackett-Luce for training this RM using that human preference data.
Got it.
And the scalar score from the RM, this single number, that's the reward signal that the main language model will try to maximize in the next step.
And step 3 is where the actual RL magic happens.
Yes, RL fine-tuning. Here you use an RL algorithm, proximal policy optimization, PPO. It's a really common one discussed in the sources.
The DPO, okay.
To train the main language model. So the LLM generates responses, the reward model scores them based on predicted human preference,
Uh-huh.
and the LLM updates its internal workings based on those scores, aiming to generate text that gets a higher and higher reward. It's this iterative loop. Generate, score, learn. Generate, score, learn.
Okay, so the LLM is literally learning to make sequences of decisions, picking tokens that get the thumbs up from the human proxy reward model.
Precisely. And the sources also point out that these reward models aren't necessarily static, like trained once and done.
Oh.
They can be updated over time with new human feedback, especially as the language model itself gets better and maybe starts exhibiting new behaviors. This helps prevent issues like reward hacking.
Reward hacking, like gaming the system.
Yeah, exactly. Where the model finds clever ways to get a high score from an imperfect reward model without truly being helpful or aligned with the original intent. So updating the RM keeps it honest, so to speak.
Okay, that makes sense. So moving on to specific techniques mentioned for that RL step, PTO sounds like a major one for this RLHF process. What's the key idea behind PPO?
PPO, proximal policy optimization, yeah, it's very popular. Its core idea, based on what we read, is to make the policy updates how the model changes its strategy more stable.
Stable how?
It uses a technique that essentially clips or limits how much the model's strategy is allowed to change in any single update step.
Like putting bumpers on a bowling alley to keep it from veering too wildly.
That's a great analogy. It keeps the training process from going completely off the rails, especially when the reward landscape might be complex or noisy. It ensures the policy updates stay within a trust region.
A trust region.
Yeah, it balances the need to explore potentially better strategies with the need to maintain stability, which is super crucial when you're training these enormous complex models.
And the sources mentioned another method, TRPO, as a kind of precursor.
Yes, trust region policy optimization. It has a similar goal-stable updates within a trust region, but it uses a more, let's say, mathematically complex method to calculate that region, often involving KL divergence constraints.
Okay.
The sources note that while TRPO might have slightly stronger theoretical guarantees on paper, PTO is often preferred for large-scale LLMs because it's simpler to implement and generally more computationally efficient in practice while still performing really well. Simpler often wins at scale.
Got it. So PPO and TRPO are about optimizing the language model's strategy using that reward signal from the RM. But the sources also describe methods that skip training a separate reward model altogether.
Yes, these are really interesting alternatives that directly use the human preference data without needing that intermediate RM step. Direct preference optimization, or DPO, is a prominent example.
DPO. Okay, how does that work without a reward score?
Well, instead of learning a scalar reward score first, DPO directly optimizes the language model's policy based on those pairs of preferred and non-preferred responses that humans provided.
Directly from the comparisons.
Exactly. It uses a specific type of loss function, basically, the objective it's trying to minimize during training, that encourages the model to increase the probability of generating the preferred output relative to the non-preferred one for any given prompt.
Ah, so it learns the preference relationship directly.
Yes, it effectively learns the human preference relationship directly from the comparison data and applies it to guide the model's generation policy.
That sounds, well, much more direct than the three-step SFTRM-RLHF process. Maybe simpler.
It certainly removes the complexity of training, validating, and maintaining a separate reward model, which can be quite involved. The sources also mention group relative policy optimization, or GRPO.
GRPO?
Yeah, apparently used in some models like DeepSeek. It leverages comparisons within groups of responses, not just pairs, to derive a kind of relative advantage signal. This can help train the model efficiently while still capturing more fine-grained preferences between multiple options.
Interesting. So groups instead of just pairs.
Right. And another one mentioned briefly is odds ratio preference optimization, ORPO, which optimizes based on the log odds ratio of preferred versus non-preferred outputs in those pairwise comparisons. So yeah, several ways to use preference data directly to shape the model's behavior.
Okay, we've talked a lot about aligning models with human preferences, making them helpful, harmless, honest. Now, how does post-training help models with something like reasoning? That feels like a different kind of challenge than just generating polite or helpful text.
It is, and post-training is absolutely critical here too. The sources describe several ways models are specifically trained or prompted to reason better after that initial pre-training.
Like I saw something called cold start RL.
Yes, exactly. This is often an initial phase used before the full RL fine-tuning we just discussed, especially as the goal is complex reasoning. You use a small, very carefully curated data set, often containing chain of thought or COTI examples. These are examples where the reasoning steps are explicitly laid out.
Ah, like showing your work in math class.
Pretty much. This early exposure helps stabilize the model and teaches it the structure of breaking down problems, thinking step by step, and showing its work. It gets the hang of the format first.
So it learns the how of reasoning first before optimizing the quality.
Exactly. It builds a stronger foundation.
Yeah.
Then you can move into what the sources call reasoning-oriented RL. This involves designing reward signals or training objectives specifically to encourage logical, multi-step thinking.
How do you reward reasoning?
Well, it might involve using automated checks on the intermediate steps of the reasoning trace, not just the final answer. Or you might train the reward model to explicitly value correct reasoning processes. So you're rewarding the process, not just the outcome.
Rewarding the process, not just the outcome. Got it.
Precisely. Now, the sources also introduce a really fascinating concept called test time scaling, or TTS. This is different because it improves performance during inference.
During inference, so when the model is actually generating an answer for a user.
Yes, exactly, without changing its core trained weights. It's basically about applying more computation at the moment you need a specific answer, making the model think harder in real time.
Interesting. So you don't retrain the model, you just use it differently.
Right. The material suggests TTS can make smaller models competitive with much larger ones on certain types of tasks, especially easy or intermediate ones, and sometimes more efficiently than just training ever bigger models.
But pre-training is still key for the really hard stuff.
Oh yeah, pre-training is still essential for foundational intelligence, broad knowledge, and tackling the very hardest problems. But PTS is a powerful way to boost performance for specific queries or problems when you need it.
What are some simple TTS methods mentioned?
A basic one is best event sampling, often called BON. You just have the model generate several possible responses and outputs for the same prompt.
Okay.
And then you pick the best one using some quality metric. This could be a simple rule-based check, or maybe even that reward model we talked about earlier. WebGPT used this approach.
So generate a few options, pick the best. Seems straightforward.
It is. It could be a simple alignment method too, though you still have to watch out for that reward hacking issue. The model might optimize for the metric you use to pick the best rather than true quality if the metric isn't perfect.
Right. And self-consistency, what's that?
Self-consistency is particularly useful for reasoning tasks. The idea is to have the model generate multiple different reasoning paths to solve a problem.
Multiple ways to get to the answer.
Exactly. And then you simply take the majority vote on the final answer that appears most frequently across those different paths.
Ah, consensus.
Right. The sources highlight that its main strength is that it requires no extra training or reward models. just more sampling during inference time. It's a clever, compute-based way to get more reliable answers for reasoning tasks.
Okay, so beyond just generating multiple options and picking, the sources mention more advanced search-based reasoning methods, right? These sound more involved.
Yes, techniques inspired by classic AI search and problem solving. Tree of thoughts, or TOT, is a big one. It generalizes that chain of thought idea we mentioned.
How so?
Instead of just one linear reasoning path, TOT explores multiple potential paths simultaneously, like branches of a tree. At each reasoning step, the model can generate several thoughts or next steps.
Okay.
It can then evaluate how promising each thought is, and crucially, it can even backtrack if a particular reasoning path seems to be hitting a dead end.
Oh, backtracking. Like humans do when they realize they made a wrong turn solving a problem.
Exactly. It mimics human brainstorming and problem-solving strategies much more closely than a simple linear chain.
And graph of thoughts, GOT, takes that even further.
Yes, GOT uses a more flexible graph structure instead of a strict tree. This allows for more complex operations. For instance, different reasoning paths that arrive at the same intermediate conclusion can be merged together.
Merging paths. Okay.
You can also have cycles, allowing thoughts to be iteratively refined, and you can explore connections between ideas more dynamically. The sources suggest GOT can be more efficient and adaptable than TOT because it avoids redundant calculations by merging paths and allows for richer interactions between different lines of reasoning. Less rigid.
Wow, that sounds like a much more sophisticated way for the model to explore the solution space for a complex problem.
It is, and there are other related ideas too, like using the model's own predicted confidence in its outputs, maybe based on token probabilities, to guide the search or decide which paths to explore more deeply.
Focusing compute on more promising avenues.
Right. And then there's this whole area of search against verifiers.
Verifiers, tell me about those.
Okay, so here, the language model generates candidate answers or reasoning steps, but then a separate automated system, a verifier, checks their quality or correctness.
So like an automated fact checker or logic checker?
Sort of, yeah. Verifiers can be designed to check just the final answer. Those are sometimes called outcome reward models, or ORMs. Or they can evaluate each step of the reasoning process. Those are process reward models, or PRMs.
Okay, ORM for the end result, PRM for the steps along the way.
Exactly. And you can integrate these verifiers into the search process. For example, using techniques like beam search, but guiding the search beams using scores from a PRM. Or incorporating Monte Carlo tree search, a powerful game-playing algorithm, within this framework where the verifier helps evaluate the different search branches.
So the model proposes solutions or steps, and the verifier critiques and guides the search towards better ones.
Precisely. It's about leveraging that extra test time compute smartly, using automated checks to improve reliability. The sources even briefly mention an idea called self-polish.
Self-polish?
Yeah, where the model might even try to refine or clarify the problem statement it was given to make it easier to understand or solve before actually attempting the solution.
Yeah, improving the question before answering it. Interesting. Okay, let's pivot a bit and talk more specifically about fine-tuning. We mentioned supervised fine-tuning, SFT, as step one in RLHF. But fine-tuning is a broader category used for different purposes too, right? It's not just for RL.
Oh, absolutely. Fine-tuning is a really fundamental post-training technique for adapting these large pre-trained models. Think of it as specializing the generalist model.
Like instruction fine-tuning? I think I've heard that term.
Yes, instruction fine-tuning is huge. This involves training the models specifically on data sets composed of instruction response pairs. Lots and lots of different instructions.
What's the goal there?
The main goal is to make the model much better at understanding and following diverse prompts from users, regardless of the specific task, whether it's summarizing, translating, answering a question, writing code, whatever.
So it makes them better general-purpose assistants.
Exactly. This is what makes models like Falan or Alpaca or many others so good at zero-shot tasks they weren't explicitly trained on. They've been fine-tuned to be really good instruction followers in general.
And you can also specialize them for specific topics or domains.
Definitely. That's domain-specific fine-tuning. Here, you use curated data from a particular field like medicine, law, finance, scientific literature to fine-tune the base model.
Okay.
This adapts the model to the specific jargon, the concepts, the typical questions and tasks within that domain. Examples mentioned in the sources include models like BioGPT for biomedical text or Finbert for financial text.
So turning a generalist LLM into, say, a medical LLM specialist.
Exactly. Now, the catch is fully fine-tuning one of these giant models on a new data set can be incredibly computationally expensive. You might need massive amounts of GPU power and memory.
Right, not something everyone can do.
Not at all. And that's where efficient fine-tuning techniques, often grouped under the acronym PEFT, are real game changers.
PAFT parameter, efficient fine-tuning.
Yes. Instead of updating all the billions of parameters in the base model, PFT methods do something clever. Techniques like LoRa or QLoRa or prefix tuning or using adapters, they work by training only a very small fraction of the total parameters, or by adding tiny lightweight modules alongside the main model, which remains mostly frozen.
Frozen meaning its original parameters aren't changed.
Correct. So you only train these small added parts, or a small subset of existing weights.
Which means you need way less computing power and memory, presumably.
Massively less. Correct. It makes fine-tuning much more accessible, much faster, potentially feasible, even on consumer-level hardware in some cases. Especially when you combine PFT with other efficiency tricks, like quantization QLoRa, for instance, combines LoRa with 4-bit quantization to be even more efficient.
So PFT makes specialization practical for many more people and organizations.
Absolutely. You get specialized models without the huge cost and resource requirements of full fine-tuning.
What are some of the tricky parts or challenges with fine-tuning, though? Even with these efficient PEFT methods, it can't be perfectly smooth sailing, can it?
No, definitely not. The sources highlight a major one: catastrophic forgetting.
Catastrophic forgetting sounds bad.
It is. This is the phenomenon where as you train the model intensely on a new task or a new data set, it starts to forget the skills or knowledge it learned during pre-training, or even during earlier fine-tuning stages.
So learning the new stuff overwrites the old stuff.
Pretty much, yeah.
Huh.
PEFT methods, because they modify fewer parameters, often help reduce this problem compared to full fine-tuning, but they don't necessarily eliminate it completely. It's a really active area of research how to enable continual learning, where the model can keep learning new things without catastrophically forgetting the old.
Are there ideas on how to tackle that?
People are exploring things like more sophisticated training strategies, maybe curriculum learning where you carefully sequence the tasks. Also retrieval-augmented methods, which we touched on briefly.
Where the model looks things up.
Right. If the model can retrieve relevant knowledge from an external source when needed, it might rely less on packing everything into its weights, which could make it less prone to forgetting when those weights are updated.
That makes sense. If the new info is stored externally, you don't mess with the core model memory as much.
Exactly. Another critical challenge, especially when you're thinking about fine-tuning models for specific companies or even individuals using their data, is safe fine-tuning. Privacy is a big one here.
How so?
Well, if you fine-tune a model on sensitive user data or proprietary company information, there's a real risk that the model might essentially memorize some of that data.
I memorize it.
Yeah. And then potentially leak it later in its generated responses, maybe through carefully crafted prompts designed to extract information. These are called data extraction attacks.
Wow, okay, that's a significant privacy and security concern. How are researchers thinking about mitigating that risk?
There are several avenues being explored. One is using differential privacy techniques during fine-tuning. This involves adding carefully calibrated noise to the training process to mathematically obscure the contribution of any single data point, making it much harder to extract specific information later.
Adding noise for privacy.
Right. Another approach is federated learning, where the fine-tuning might happen locally on devices where the data resides, and only aggregated, anonymized updates are sent back to a central model, so the raw sensitive data never leaves its original location.
Decentralized training.
Exactly. And there are other emerging techniques too, like homomorphic instruction tuning or using differential privacy by adding noise to reward signals in RLHF. The sources generally note, though, that there's often a trade-off.
A trade-off between what?
Between the level of privacy protection you achieve and how well the fine-tuned model ultimately performs on its task. Stronger privacy guarantees might sometimes come at the cost of slightly reduced accuracy or utility. Finding the right balance is key.
So you might have to carefully weigh the privacy needs against the performance requirements for a given application.
It's definitely a key consideration and an area of ongoing work.
Okay, so with all these different ways to post-train models, RLHF, DPO, various fine-tuning methods, reasoning techniques, how do researchers even know which techniques are working best? How do they compare performance objectively?
Yeah, that's crucial, right? Evaluation is essential. You need good benchmarks. The sources we looked at actually list quite a few categories of benchmarks that are commonly used.
What kind of categories?
Things like reasoning benchmarks, obviously. RL alignment benchmarks, which specifically measure how well the model aligns with human preferences using methods like RLHF. Multilingual abilities, general comprehension across different subjects, dialogue skills, how well models work with search engines, even things like story generation or recommendation quality, and some emerging benchmarks trying to evaluate values.
A wide range, and different ways to actually do the measuring on these benchmarks.
Yes, broadly two types mentioned. Point-wise evaluation, where you score a single model output based on some predefined criteria like, is this math answer correct? Is this summary accurate?
Okay.
And pairwise evaluation, which is more common for subjective qualities like helpfulness or harmlessness. Here, humans, or sometimes another AI model, compare two different outputs generated for the same prompt and simply say which one they prefer.
Preference judgments.
Exactly.
Right.
That relative judgment is often easier and more reliable for humans to make than assigning an absolute score.
Can you give us a couple of concrete examples of benchmark names we might hear about?
Sure. For reasoning, you often hear about benchmarks like math or GSM-8K, which focus on math word problems. For RL alignment, datasets like HelpSteer or Anthropic's HHRLHF dataset, which stands for Helpful and Harmless RLHF, are widely used based on collected human preference data. MMLU is a very broad, popular benchmark for general comprehension, covering tons of subjects from history to computer science. And for pairwise evaluation, Chatbot Arena is a well-known example where users interact with anonymous models and vote on which one gave a better response. That generates a running leaderboard based on direct user comparisons.
Got it. So these benchmarks provide the essential yardstick to measure progress and compare different post-training approaches?
Exactly. Without them, it's hard to know what's actually working.
So looking ahead now, based on everything we've covered from the sources, what are the big trends we should be watching in this whole space of LLM post-training? Where is it heading?
Well, the sources definitely highlight several key directions. Reinforcement learning seems poised to become even more central, moving beyond just simple alignment for helpfulness towards tackling more complex tasks and maybe even long-term goals.
More RL. Okay.
Reward modeling is also getting more sophisticated. People are working hard to make those reward models more robust, less susceptible to hacking by the LLM, and maybe better able to capture nuanced human values. Though creating perfect reward models remains a huge challenge.
Right. And what are the reasoning side?
The reasoning methods we discussed, like tree of thoughts, graph of thoughts, and other search strategies, are definitely evolving. The push is to make models think more deliberately, explore alternatives, and verify their steps. A key challenge there, mentioned in the sources, is efficiently guiding that search and knowing how sure the model should be about its reasoning steps. Uncertainty estimation is important.
Making the search efficient and reliable.
Yeah. And alongside capability improvements, there's a huge growing emphasis on safety, robustness, and making these increasingly complex models more understandable or interpretable. That's critical for trust and deployment.
Makes sense. What else?
Personalization and adapting models to specific domains or individual user needs is also a big trend, which goes hand in hand with needing to solve those privacy and safety challenges during fine-tuning that we talked about.
So the big challenges seem to be making these powerful techniques more reliable, robust, safe, and private as they get deployed more widely.
Exactly. The sources also touch on some really exciting emerging areas, things like multi-agent systems, where you might have multiple AIs collaborating or debating to solve a problem. Frameworks like MALT or ACC debate were mentioned.
Multiple AIs working together.
Yeah. Or bringing in multimodal information like images or diagrams alongside text to improve reasoning. MVOT, multimodal verify on the fly, was an example. And as we mentioned, retrieval-augmented techniques continue to be important for keeping models updated with fresh information without the need for constant, expensive retraining from scratch.
Lots happening. So where does all this leave us? We've taken this deep dive into the world. After pre-training, we've seen how reinforcement learning helps models learn human preferences.
Through things like RLHF or DPO.
How different fine-tuning methods adapt them to specific tasks and topics, making them specialists or better instruction followers.
Using techniques like BFT to make it efficient.
And how advanced reasoning techniques like tree of thoughts and using verifiers during test time can make them reason more effectively, more like humans do.
Yeah, understanding this whole post-training landscape is really the key, I think, to understanding why the LLMs you use every day behave the way they do, and how they're constantly being shaped and improved behind the scenes.
It's not just about the initial massive data dump.
Not at all. It's that crucial second stage, the post-training, that often turns raw language capability into genuinely useful, aligned intelligence. It really is the shortcut, to being well-informed about this critical aspect of modern AI.
It definitely makes you appreciate the continuous refinement happening. It also makes you wonder, though, as these models get smarter and seemingly more aligned through all these sophisticated techniques, are we reaching a point where they don't just predict text anymore, but genuinely begin to reason and adapt in ways that will fundamentally change how we interact with them?
That's the big question, isn't it?
Yeah. And what does that relentless pursuit of more capability versus the careful, painstaking crafting required for alignment, safety, and privacy?
Yeah.
What does that ongoing tension mean for the future trajectory of AI? Where does the balance lie?
Fascinating questions to consider long after this discussion.
Indeed. Well, thanks for joining us for this deep dive today.
Always a pleasure. Thanks for having me.